All right. Good afternoon, everyone, and welcome to the final PGSS talk of this summer. My name is Blake, and I work with the rest of my organizing team for PGSS and Grad Council, or Physics Graduate Council, I should say, to give you this talk. Quick thing, real quick. If you haven't already, or if you joined later and you didn't hear the announcement, could you please navigate over to the chat window and sign in so that we can document your attendance. And then also we have a feedback form for a speaker that you can fill out while they're giving their talk or after the talk. So that way they can get some feedback and improve upon their talk. I also wanted to announce that unless you are a speaker, to keep your microphones off during the talk because we are recording it and we don't want to have any, I guess, interruptions during the talk. So that way the recording keeps nice and smooth. With that being said, today's talk is going to be presented by Angela Chen of the Physics Department. She will be presenting challenges to LCDM and how we explore beyond. Angela, you can take it away.
Okay. Thank you for introducing, and thanks everyone for coming to this talk. So today I'm going to talk about the challenges to Lambda CDM and how we explore beyond this standard cosmology model. So actually, the main goal is to get it through to everyone that's what we're doing in cosmology and astrophysics. So actually, I would say if you have any questions or follow-ups, you can ask me anytime. Okay, before start, a little bit information about myself. So I'm a physics PhD working in cosmology with Dragon Filter and mostly working with dark energy survey, large-scale structure survey. Okay, to begin with, so what is Lambda CDM model? So I don't know if you ever heard of it, but Lambda CDM model is the most successful cosmology model so far, and it's like the standard model in cosmology. The following paragraph are all copied from Wikipedia. So it's a parameterization of the Big Bang cosmological model, and it basically states that our universe contains three components. So first is lambda, denoted by lambda, is the dark energy, negative pressure component, and we have cold dark matter, a matter that doesn't interact with others through any standard model forces, only through gravitational forces. And the last one is the ordinary matter, consists of our that forms our daily life, our Earth, our life, and also radiation is also included in the third component. So why is Lambda CDM successful, and what's the observational evidence of Lambda CDM so far? So it's kind of amazing if you think about how we get to know like things happen, what happened in millions of light years, millions of years, billions of years in the past. So it's mostly through the observation of the expansion of the universe. Okay. Sorry. Actually, are there any questions about Lambda CDM model? Okay. I'll continue. Maybe like if there's any questions, I can answer in the question time. So the observational evidence of Lambda CDM mostly come from the expansion history observations. So the theory of that is so we assume our universe is homogeneous and isotropic. So that gives us this metric of our universe. A is the scale factor. It's only dependent on time. So that's why the universe is homogeneous and isotropic. So given this metric, we know we have Einstein equation. And one component of the Einstein equation, the Friedmann equation, connects the universe components and their equation of states to the expansion history, which is the Hubble parameter here. Hubble parameter is defined as the scale factor time derivative over scale factor itself. And Friedmann equation is the second equation on this slide. It connects on the right-hand side the matter, not just matter, all the universe energy density and the expansion history. So, and for a curved universe that contains radiation matter and dark energy, we know how each of these components energy density scales with a scale factor, and that brings us to the third equation on the slide. And you can see from this equation that the radiation energy density scales with scale factor by -4 power, and for matter, cold matter or ordinary matter, the energy density scales with a to the -3 power, and so the small k here is the curvature of the universe. It could be +1, 0, or -1, corresponding to positive and flat, positive curvature and flat and negative curvature universe. And the dark energy, its energy density is completely independent from on the scale factor. So that's the most famous feature of the dark energy. It's like the energy density of the space-time itself. So, and given this equation, if we can measure the expansion history of the universe, namely how the scale factor evolves with time, we can fit this third formula and find out how much radiation and matter and dark energy and the curvature of the universe we have in the universe. And so one way of observing the expansion history is through the supernovae Hubble diagram. Okay, a little bit more comments here. So the scale factor, usually in observation, will transform it into, translate it into redshift. So redshift, it's defined in the normal way. So it's the ratio between, the difference between the observed and emitted wavelengths over the emitted wavelength. And because the universe is expanding, so if we normalize the scale factor at current time to 1, then a light signal emitted at the time when the scale factor is A will experience a redshift equal to 1 over A minus 1. So and redshift it's a quantity easy to observe. Given featured spectrum or the emission line, we can easily measure the redshift. And in the observable, the time usually is it's interchangeable with distance because light speed is fixed. So instead of like directly measuring the scale factor and time relationship in the observables, most of the time we're looking for the relationship between redshift and distance. And supernovae could Hubble diagram could give this information. So type 1a supernovae, this kind of astronomical objects are called standard candles because their magnitudes it's a fixed value. And by observing the flux at the Earth, we could infer its distance. And this supernovae usually this kind of astronomical objects they're hosted by a galaxy, and they're always something we can measure the spectrum to determine their redshift. And thus we get observed relationship between redshift and the distance to the supernovae. And so by fitting this curve, the free parameters being the components in the universe, we exclude, you can see we can exclude the universe without any dark energy by many sigma significance. So that's one of the concrete evidence of the lambda CDM cosmology. Our universe indeed have a large portion in dark energy and cold dark matter. And another observational evidence of lambda CDM comes from cosmic microwave background. It's temperature and polarization power spectrum. So the Big Bang theory tells us the universe starts from a hot plasma, and as the universe expands, this plasma cools down, and at some temperature, finally the photon decouples from the rest of the ordinary matter. That decoupled photon free stream after the time of recombination and reach to us without any like interaction. So so there are surveys like Planck observing the temperature fluctuations of microwave background and calculate their two-point correlation functions. So the figure here it's this correlation functions in the harmonic space transferred into L space, momentum space. It's and you can see it's very well fitted by the lambda CDM model. And how and why lambda CDM it's probably the only model that or any like slightly deviation from lambda CDM is the only one that could fit this spectrum. So because in the plasma before photon decouples, there's this sun horizon in this plasma, the sun space. So there's small fluctuations in this plasma, and there's a characteristic sun horizon. So as the photon decouples, this kind of sun horizon scale is inputted into its temperature fluctuation map. And this scale, the sun horizon at last scattering surface, it's like a slender ruler in the cosmology. So, but what we could measure model independently, it's the angle of this scale in the sky. So that means like the light it traveled, the distance it traveled after last scattering has to like agree with your model very well, so that the angle we measured like would agree with the theory prediction. And so and you can see we have a lot of data points on this spectrum, and we get a very tight constraint on lambda CDM parameters from CMB. But what could be wrong about this model? So it's been a very successful model, and I'm still amazed by like how well lambda CDM predicts the cosmic microwave background. But recently we got more and more precise measurements on the cosmological observables, and there start to this Hubble tension start to appear. So basically, what's this Hubble tension in the hot debate is that the late time measured local measurements of the Hubble constant, it's different from the early time measured Hubble constant. They are in the discrepancy at about 4 to 5 sigma level currently, and people are discussing if it's due to any systematics for beyond lambda CDM model physics. But here I'll start with like how concrete this tension is, or how not concrete this tension is, depending on your judgment after I show you what we got at hand. So the local measurements of the Hubble constant come from, like I described before, the redshift plus distance relationship. So redshift is easy to measure. All of the methods listed here are mostly crafted for concrete measurement of the distance. So the first one is the most famous one. It's through the standard candle distance ladder. So like I said before, we got supernova and type 1 supernovae. For example, type 1 supernovae, we assume it's a standard candle, and we can calibrate this standard candle through in our vicinity of the observers through like parallax in Cepheids. Then we invert the distance from the observed magnitude, observed flux from a distant supernovae into the Hubble flow. And we also have strong lensing. So I won't go into the details because I'm not familiar with this either. But consider so strong lensing caused by the gravitational lensing. You can analyze the geometrics of this strong lensing system, given some of the observables of the angle between the lens object and images, and then view them, and then you invert the distance to the source of this lensing system from there. There's also this water megamaser. Yeah, I'll skip the details. But the bottom line is that so far there have been a lot of different methods, completely independent methods to measure the local Hubble constant. and they gives us pretty consistent results, as I'll show you later. And another way of measuring the Hubble tension is through the model fitting, lambda CDM-based model fitting on, for example, CMB. So let me remind you, like the angle corresponding to the sound horizon is the most model independent, most concrete measurement we got from CMB. So if you want to modify anything, you have to make sure you fix the theta in your model. So the Hubble tension. So here's a picture I took from a tension conference last year. As you can see, all the late time measurements of the Hubble constant is higher than the early time measured Hubble constant. It's at 4 to 5 sigma level, and both the early time measurements, although only Planck is listed here, but we got other like CMB measurements like ACT currently, and also that's combined with BAO and BBN. So all of these early time measurements are also consistent and consistently giving a lower Hubble constant. And we'll ask, what's the solution about this? Like 4 to 5 sigma is not something you could just ignore currently. And of course, first thing we'll turn to is a systematic errors. So like someone proposed, like what if we're living in a local void? In that case, our vicinity universe will expand faster than the average. But it's statistically unlikely. So the fluctuation of the matter density field can be measured through like weak lensing and clustering, and that's already been done. And given this fluctuation of the matter density field, we could calculate how much uncertainty this fluctuation would bring into the Hubble constant, local Hubble constant measurement. So that only costs about 0.6% uncertainty in the Hubble constant. But the local measurement in the last slide itself, it's about at the position about 1%. So and the difference it's already about several percent difference. So that means like in short, we need about 10 to 20 sigma like uncertainty caused by this local voice to cover the difference. It's statistically not likely. And so another possible systematic error is the supernovae calibration error. So like me, like any person not in the astronomy might question like how standard this standard candle is. Well, at least for any calibratable like close supernovae we observed like pretty consistent magnitude of the type 1a supernovae. But there's also still possibility that this magnitude it's a redshift dependent. There's a redshift evolution of this type 1a supernovae magnitude. In that case, it's no longer standard, and the distance measured by this standard candle distance ladder is questionable. So it's still possible, but there's no evidence, and as I said, all calibratable objects are standard, and there are other local measurements, like shown in the previous slides, that's independent from the supernovae. This other local measurements of the Hubble constant also give us consistently higher value. And there's also possibility that the redshift measurement, there's systematics in the redshift measurements. But it's hard to imagine that this kind of straightforward measuring process would bring large systematics. All you need is a spectroscopic measurement of a line or a featured spectrum we know and measure its redshift in the spectroscopic observations. And there's of course possibility that there are other systematics we don't even know about, we don't even consider about. But at the meantime, we could possibly also start to think about what if it's some intrinsic defects about lambda CDM. We need some beyond lambda CDM models to fix the Hubble tension. Hubble tension is only one of the most statistically significant tensions I discussed here. There's also some slight anomalies, like the late universe, like clustering and weak lensing surveys consistently measuring slightly lower matter fluctuation magnitude than CMB, and some other slight anomalies. All this calls for like beyond lambda CDM model. So, and before we go into like detailed analysis, what kind of model do we need to relieve this tension? So theta is something, a sun horizon angle is something we measured model independently. So we want to fix this thing fixed. Take this thing fixed in our new extended model. So in that case, the things we could modify are the pre-recombination expansion history and late time expansion history, and the recombination epoch. So this when redshift goes to infinity, that means it's the very origin of the universe. The sun horizon, this is the integral of time over the sun speed up until the decoupling of the photon. And the lower part, the denominator part, is the late time geometry. How long this photon traveled from the for example, the recombination to us. And for any beyond lambda CDM models, the difficult part is that you have to be more successful than lambda CDM. Like lambda CDM predicted all of the following observations, and they're all by far pretty in pretty good agreement with lambda CDM, except for the Hubble tension that appeared recently. So first is the cosmic microwave background temperature and polarization, and secondly we have to like not deviate from the geometry of the lambda CDM too much. And there's also this large-scale structure growth. So the galaxy clustering and wave cleansing. That's what this is measuring. So we know we have a lot of galaxies in the sky, and their distribution and the wave cleansing slightly distorted galaxy shapes tells us like basically how much the matter field is matter density field is fluctuating. There are more like other small scale observations. So if you want to propose any like beyond lambda CDM models that fix the Hubble tension problem, you have to fit to all these observations and given no worse than lambda CDM fitting to them. So one example, my project currently is to test decaying dark matter model as a potential solution to Hubble tension. So this decaying dark matter cosmology model states that the universe contains not cold dark matter, but decaying dark matter and radiation and dark energy. So so that means the density, comoving density of the dark matter evolves with time by this ansatz. So this ansatz is plotted on the figure on the right. If it's cold dark matter, it would be a flat line at 1. So the comoving density, which is defined as basically the density times scale factor to the third, it's a constant for cold dark matter. In this decaying dark matter model, the density of the dark matter decays. And the second equation tells you all this decayed energy density goes transferred into dark radiation. In this sense, I introduced two extra parameters. First is theta, the decayed fraction of the dark matter. So the fraction between the amount of dark matter at the beginning of the universe and current time, it's 1 plus theta. It's 1 plus theta. So, and kappa is a decay rate parameter. The higher kappa is, see, the faster the decay happened. And what could this decaying dark matter and radiation be? So at least we want to find some like physical motivation for this model. Although it's a phenomenologically motivated model. So it could be Susi particles and the lightest Susi particle, and it could be fifth source fermion and boson, and it could even be primordial black holes. So you might remember some time ago from the LIGO gravitational wave observation that the summation of the summation of the mass of the two rotating black holes, could be about like 30 solar masses, and after they collide and emitting the gravitational wave, their mass decrease. So all this energy loss was most of the energy loss in this process is radiated into gravitational wave. And gravitational wave is by definition could be a dark radiation. It's relativistic. It's a radiation, and it's not detectable by particle detectors. And even more, it could be so the Hawking radiation could radiate out any like light beyond standard model particles from primordial black holes. So these are some physical candidates of this decaying dark matter. But the cosmology implication of this dark matter, decaying dark matter model actually doesn't care about what's the nature of this decaying dark matter. It just tells us there are more matter and matter density fluctuation in the past and less current time, which it's a slight anomaly we observed recently. And in the late universe, dark energy takes over faster, so the accelerated expansion happens earlier. That could lead to a higher Hubble constant. And also it costs more lensing on CMB because the gravitational potential changed more. The gravitational potential caused by dark matter decayed away. And one of the things Planck observed recently is that there are slightly higher lensing magnitude for CMB than what would be expected in lambda CDM. So all this are the motivations for decaying dark matter model, but it doesn't mean that it's bound to be a successful model, because all this effect, like said before, the cosmology of the ripples so far are a lot of them are the power spectrum of the fluctuations. So when you want to get some of the features right, you don't know if it will affect other features in the power spectrum. You have to run a full analysis on the data sets to get to know whether your model is good at getting this feature you wanted while keep other things perturbed. So for the test of decaying dark matter model, I combined these data sets. So first is galaxy clustering and wake lensing spectrum from jets. And I got the Hubble diagram from Pantheon and CMB temperature polarization and lensing power spectrum from Planck here. And lastly, I got the baronic acoustic oscillation compressed data from these three surveys. We then run Markov-Chen Monte Carlo on all this data to find the best fit in the decaying dark matter model. I can't show you the results because it's still in internal reviews of dark energy survey. But some preliminary thoughts here. So the decaying dark matter model is only as good as lambda CDM. Globally, we didn't find any significantly better fitting for all the observations. We got the tightest constraint on the effective decay width of the decaying dark matter model, and the overall tension between dark energy survey, which is a late universe probe, and the external datasets, which is dominated by CMB from Planck, reduced. but that could mostly due to contour broadening, because as presented before, we introduced 2 extra free parameters, the decay fraction and decay rate in this model. Some future works to finish. In the process of working on the decaying dark matter model, I realized the main concern on this kind of beyond lambda CDM model analysis is that there are some implicit assumptions in the pipeline, because you see the data, the observable data is very complicated to analyze, and sometimes people make implicit assumptions under lambda CDM. But for any tests of the models beyond lambda CDM model, we have to reverse that and carefully build the whole pipeline design the whole pipeline for the beyond lambda CDM model. And of course, there will be more data in better precision in the next few decades. There will be a large amount of data pouring in cosmology, and that's very, very exciting. Okay, that's all the presentation now. That's all the slides now. If you have any questions, you can ask me.
Thank you so much, Angela. As she pointed out, if you guys have questions, you can raise your hands, and when I can call on you, and you can unmute yourself if you're muted and ask your question. So if any of you guys have questions at this time, now would be the time to unmute yourself and ask. It doesn't look like there are any questions. So I guess, Angela, thank you so much for giving your talk. For those of you that are still there, if you haven't already signed in, please do sign in and make sure to fill out the feedback form in the chat window as well for Angela, so she can improve her talk, or tell her that she did a wonderful job if you think that there's nothing that she needs to do to make this talk better. Thank you all for coming. Thank you guys for supporting PGSS talks this summer. And I guess we'll see you next year if you decide to come again. Thank you, guys.
Thank you.